Hello and welcome back. So what I want to talk to you about in today's electronics tutorial video is buck converters. But I don't want to go over the entire converter. I want to focus on one particular component. So if we have a look at the generic converter, what it looks like, so what we got here on the Wikipedia page about it, we see that it's quite a simple circuit. So you got your input supply, output load, a diode, an inductor, capacitor, and a switch. Now, the way it's represented here in this schematic is by a mechanical switch. But in real life, you're not going to be building your converter with mechanical switches. I mean, you could try, but that's not going to work out very well, and you're probably a normal person, so you're not going to go into that. On the other hand, what you will do is replace this switch with an electronic switch. And what I want to do today is look at the ways you can actually drive the high side transistor switch. So go over the ways of doing it the right way and the not so right way. So if you're curious about that and much more, then keep watching. So let's start off by talking about the particular type of transistor used in the converter. Now, you can use bipolar transistors, field effect transistors, IGBTs, you name it, you can use any of them in a buck converter. But in particular, today I want to focus on MOSFET type of transistors. And to start things off, I want to look at how you can use a P-channel MOSFET as a high side driver in your buck converter. And for that, let's turn to the circuit simulator. LTSpice, of course. So what I got here is the generic power stage for a buck converter using a P-channel MOSFET, of course. And to drive it, I'm using one of the simplest types of circuit you can use. Basically, I'm taking the signal from my signal source and driving it through an open collector type of driver. And this will drive the gate of the transistor. And if we run this thing and look at the voltage in the switching node compared to the voltage in the input signal, we can see that when the input signal is high, so is the voltage in the switching node, so the switch turned on, and then when the signal is low, the voltage in the switching node is low. So the circuit seems to be working. Let's just make sure that everything is okay by looking at the circuit in real life. So what I got here is basically the circuit that we've just simulated. I'm taking a signal from the signal generator, passing it through the first channel just so we can see it on the oscilloscope, and then using it to drive my high side P-channel transistor. Then I have the entire power stage of the buck converter, and then this is connected to an active load. On the other side, of course, I have some filtering capacitors, but I put them there just so that it's nice and tidy. So if we run this thing, we see that the active load is on, so seems to be working. And now we can take the oscilloscope probe and look at what the switching node looks like in real life. So we can see, just like in our simulation, that when the input signal is high, so is the voltage in the switching node, and then they both turn low. But we see one more thing, which we shouldn't be seeing. There's quite a lot of delay in between the two signals. And this ends up affecting the duty cycle. Even though I'm driving the circuit with a 20% duty cycle, I end up having 63% because of this delay. And even worse, if I mess around with the switching frequency, say I go from 50 kHz to 100, the switch is now barely switching. So you can see that it's trying to turn off, but it's not really getting there. And if I turn up the frequency a bit more, go to 200 kHz, the switch is completely on. It never has time to turn off. And this is not a good thing. The voltage in the switching node should follow as closely as possible the input signal. So how do we fix this? Let's turn back to the simulation for this. So the problem we're getting here is that even though the voltage in the switching node turns high almost exactly as the input signal does, we can't say the same thing about the signals going low. Difference being that to pull the signal high, you need to turn on the transistor, and you're doing this using the low side transistor in the circuit. Whereas to turn it off, you're relying on this resistor. So the easiest way to fix this problem is to go from an open collector type of driver to a push-pull type of driver. Basically what I've got here. So I kept the open collector type of driver, but I'm using it to drive a Class B amplifier, which works like a push-pull stage. By doing this, the voltage in the gate of the transistor turns from this sort of shape that we had in the first case to a completely different shape. So now we can see that both the turning on and the turning off parts are very clear and very sharp. You don't have this slow turn off phenomenon. And that is because we're actively turning off the transistor by using the high side transistor. And by doing this, we can now compare the input signal to the signal in the switching node and see that we have a very nice, very straight edge. So we still have a bit of delay. That's because the components have a bit of turn on and turn off delay, and that's perfectly normal. But at least the edges are nice and sharp. And the most important benefit of doing this is that it improves power dissipation. So if we look at our first circuit, during this turn off phase, so when the voltage in the switching node goes low, the power dissipation is quite high and for quite a lot of time. On the other hand, in the second case, if we look at the moment in which it turns off and we look at the power dissipation, we can barely see a very thin line in here. So if we zoom out and compare the power dissipation on the two transistors, the first case and the second case, in the first case we're dissipating around 600 milliwatts, whereas in the second case it drops down to 148. So by improving the switching characteristics of the transistor, you can greatly improve the converter's efficiency. And this is basically how you should drive the high side P channel. So using this sort of push-pull driver, you can drive the transistor at much higher frequencies and much more efficiently. The open collector type of driver can work if the switching frequency is extremely low. Now, this about covers the main ways to drive the P channel. But what about the N channel transistor? I mean, normally in converters, you will find N channel type of MOSFETs, not P channel. And the reason for that being cost related. It's much more expensive to make a P channel transistor than it is to make an N channel transistor. And that is because of the process of making it. So let's look at how you can drive N channel transistors now. And here we can see the basic circuit built with an N channel transistor. It looks quite similar with the previous one. The only difference being that I swapped the source and the drain of the transistor, but other than that, it's the same circuit. But does it work? Well, if we run it, we can see that the switching node is still switching. But let's just see how well this is working in a practical circuit. So what I got here is the same setup as before, only difference being that I swapped the P channel for an N channel. And if we run this thing, we see that the output is working. And if we look into the switching node, just like we've seen in the simulation, it's switching. Difference being that this time we have an inverted switching node compared to the input signal. That's because we swapped the P channel with the N channel. We still have this slope going on, so the transistor is not turning on very quick. That can be fixed using the push-pull type of driver. And it's important to mention here that the slope at which the transistor turns on, when only the resistor is driving it, is dependent on the capacity of the gate. So if you have a transistor with a very large gate capacitance, then it will have a very slow turn-on slope. If the gate capacitance is very small, then the slope will be much faster. So there's one more thing you might notice, and that is that the high voltage in the switching node is around 8.2 volts, whereas the supply voltage, I have it at around 10. So we've lost 1.8 volts somewhere along the way. And that's not a very good thing. I mean, 1.8 volts is a large loss, and it's completely unacceptable. I mean, the slope we can fix with the push-pull driver, but not this. Let's go back to the simulator, see exactly what's going on. So if we come back here and we look at the input voltage, we see that here we have 3 volts of difference between the input voltage and the voltage in the switching node. Now this voltage depends on the exact transistor that you're using, and it's the threshold voltage needed to open the transistor. So for the MOSFET type of transistor, you will have a gate threshold voltage somewhere in between 1 and 3-4 volts, it highly depends on the transistor. So this particular transistor that I have here in the simulation has a gate threshold voltage of 3 volts. So the voltage in its source will be 3 volts lower than the voltage in the gate, and the voltage in the gate at the moment has a maximum of the supply voltage. So the only way to get this thing to have a higher voltage in the switching node, so to have a very small voltage drop on the transistor, would be to drive the gate with a higher voltage than the input supply voltage. So if I'm supplying the circuit at 12 volts, I will need 15 or 20 volts or something that is more than 12, more by the gate threshold voltage at least. And we can get a higher voltage with a circuit like this. So compared to the previous circuit, I added this capacitor and diode. And the logic behind this is that when the switching node is low, so at 0 volts or lower, then the diode will charge the capacitor. When the voltage in the switching node is high, then the voltage on the capacitor will be higher than that of the input voltage. This is also called a bootstrap capacitor. And if we look at how this works, so we can see that the voltage in the switching node goes up to 9 volts, but the voltage on the capacitor, at the moment when the voltage in the switching node is high, gets up to 21 volts. So plenty enough to drive the transistor. So there's just one small modification that needs to be done to the circuit, and that is connect the high side resistor to this point. So to no longer drive the gate of the transistor from the supply voltage, but rather from this bootstrap voltage. And by doing this, the voltage in the gate will go from 0 to 20 something volts, so double that of the supply voltage in this case, and that means that the voltage in the switching node this time will end up at the supply voltage. So we no longer have that 1.3 volt voltage drop on the transistor. And this way we can get the supply to work efficiently. So this is the way to get the voltage drop on the transistor to be as low as possible, and to get the rising and falling slopes on the switching action nice and straight, you will need to add the push-pull type of driver. So a circuit that looks like this. So this is the complete circuit for driving the N-channel properly. We have our bootstrap assembly built to have a higher than the supply voltage. We have a push-pull driver to drive the gate. And if we run this thing, we see that the voltage in the gate has a very sharp turn on and turn off. And also the voltage in the switching node is in opposition to the input signal. But again, we have the very nice, very straight edges. So very fast turn on and very fast turn off. And this leads to quite a small power dissipation. So we can see that we have large power spikes, but these are of very short time duration. And that about covers both P-channel high-side drivers and N-channel high-side drivers. So hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos. And see you next time. Bye bye.